This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. You can take our paid version with the Unlimited Testing Center, but you can also take our free version that is completely free without the Unlimited Testing Center. Also, if these videos have been helping you at any time, you can also go there and pay it forward to see it head on to the next generation. I am the Electrical Code Coach. Let's go ahead and get to it. Welcome back. This is week 11 of the Master Electrician Exam Prep Series. Really excited to get into it this week. We're going to be dealing with bundling adjustments and temperature corrections. Let's get to it. What is the allowable ampacity of a number 10 THWN-2 copper conductor that's installed in a pipe with 45 current carrying conductors? When we're doing temperature corrections and bundling adjustments, we're going to start in the 90° C column. So we find that a number 10 in the copper 90° C column is good for 40 amps. Now we're going to head to table 310.15 B3A in the 2017 and 310.15 C1 in the 2020. So we're going to find the adjustment factor for 45 current carrying conductors, and in this case it's 35%. Now we just take our original ampacity, multiply it by 0.35, and that's going to give us a new allowable ampacity of 14 amps. So this wire that was once safe to hold 40 amps in the 90° C column is now only allowed to hold 14 amps safely. And we select D. What is the allowable ampacity of a number 10 THWN-2 copper conductor that's installed in an area with an ambient temperature of 142 degrees Fahrenheit? When we're doing temperature corrections and bundling adjustments, we're going to start in the 90° C column. We find that a number 10 in the copper 90° C column is good for 40 amps. Now we're going to head to tables 310.15 B2A in the 2017 and table 310.15 B1 in the 2020. Same table, new name. We're going to find the temperature correction factor. This is our temperature correction factor table. We're going to slide down to our new ambient temperature, being sure to start on the Fahrenheit side, which is on the right-hand side of the table, because our degrees are listed in Fahrenheit for our ambient temperature. Then we're going to slide over and tee off with the 90° C column that has the correction factors in it. So we're going to find 0.65 is our correction factor. Now we're going to take our original ampacity, we're going to multiply it by 0.65, and that's going to give us a new allowable ampacity of 26 amps. And we select B. What is the allowable ampacity of a number 4 THWN-2 copper conductor that's installed in an area with an ambient temperature of 135 degrees Fahrenheit? When we're doing temperature corrections and bundling adjustments, we're going to start in the 90° C column. We're going to find that a number 4 in the 90° C copper is good for 95 amps. Now we're going to head to our respective tables, and we're going to find that our temperature correction factor for 135 degrees Fahrenheit, being sure to start on the Fahrenheit side, the right-hand side of the table, and then coming down and teeing off in the 90° C column, and we find that our correction factor is 71%, 0.71. So we're going to take our original ampacity of 95 amps, we're going to multiply it by 0.71, and that's going to give us a new allowable ampacity of 67.45 amps, and we're going to select C. Great job. What is the allowable ampacity of a 2-watt XHHW copper conductor that's installed in an area with an ambient temperature of 111 degrees Fahrenheit? When we're doing our temperature correction and bundling adjustments, we're going to start in the 90° C column. We're going to find that 2-watt copper in the 90° C column is good for 195 amps. Now we're going to head to our respective tables. We're going to find our temperature correction factor for 111 degrees Fahrenheit, being sure to start on the Fahrenheit side and then selecting from the 90° C column. We find that it's 87%, or 0.87. Now we take our original ampacity, we multiply it by 0.87, and that's going to give us a new allowable ampacity of 169.65 amps. And we select D. What is the allowable ampacity of a 2-watt XHHW copper conductor that's installed in an area with an ambient temperature of 68 degrees C? When doing temperature corrections and bundling adjustments, we're going to start in the 90° C column. We find that 2-watt in the 90° C copper column is good for 195 amps. Now we're going to head to our respective tables, and we're going to find the temperature correction factor for 68 degrees C. We're being sure to start on the Celsius side of the table on the left-hand side, and then we have to be very careful here. So we start on the left-hand side because our ambient temperature is in Celsius, but then we have to make sure that we tee off all the way over in the 90° C column. We find that it's a 58% correction factor, or 0.58. So we're going to take our original ampacity, multiply it by 0.58, and that's going to give us a new allowable ampacity of 113.1 amps. And we select A. Great job. What is the allowable ampacity of a 4-aught XHHW aluminum conductor that's installed in an area with an ambient temperature of 55 degrees C? We're going to start in the 90 degrees C column. We're going to find that 4-aught in the 90 degrees C column for aluminum is good for 205 amps. Now we're going to head to our respective tables. We find the temperature correction factor for 55 degrees C, being sure to start on the left-hand side of the table because our ambient temperature is in Celsius. Now we're going to head and tee off with the 90 degrees C column for our correction factor. We find that it's 0.76. Now we take the original ampacity, multiply it by 0.76, and that's going to give us a new allowable ampacity of 155.8. And we select B. Great job. What is the allowable ampacity of a 4-aught XHHW aluminum conductor that's installed in an ambient temperature of 81 degrees C? So we're going to start in the 90 degrees C column. We're going to find that 4-aught in the 90 degrees C column is good for 205 amps. Now we're going to head to our respective tables. Now we're going to find the temperature correction factor for 81 degrees C, being sure to start in the Celsius column because our ambient temperature is listed in Celsius. Then we're going to make sure we go all the way over to the 90 degrees C column to get our factor. We find that it's 29%. So we're going to take the original ampacity of 205 amps, multiply it by 0.29, and that's going to give us a new allowable ampacity of 59.45 amps. So this wire that was once good for 205 amps is now good for a little under 60. And we're going to select C. Great job. What is the allowable ampacity of a number 10 THWN-2 copper conductor that's installed in a pipe with 5 current carrying conductors in an area that's in an ambient temperature of 118 degrees Fahrenheit? Now you know how to do both of these independently. Now it's time to put them together. Take your time. You can do it. So when we're doing temperature corrections and bundling adjustments, we're going to start in the 90 degrees C column. We're going to find that number 10 in the 90 degrees C column is good for 40 amps. Now we're going to go find out our bundling adjustment. So what we're going to do is we're going to head back to our bundling adjustment table, and we're going to find out that for 5 current carrying conductors, it is an 80% reduction, 0.80. Now we're going to head to our temperature correction table, and we're going to find out that at 118 degrees Fahrenheit, the correction factor is 0.82. Now we're just going to take and bear out the math. So we take our original ampacity, multiplied by the bundling adjustment, multiplied by the temperature correction, and we're going to find our new allowable ampacity. So 40 multiplied by 0.80 multiplied by 0.82 is going to give us a new allowable ampacity of 26.24 amps. Great job. What is the allowable ampacity of a number 4 THWN-2 copper conductor that's installed in a pipe with 9 current carrying conductors in an area with an ambient temperature of 101 degrees Fahrenheit? So we're going to start in the 90 degrees C column. We're going to find that number 4 in the 90 degrees C column is good for 95 amps. Now we're going to figure out our bundling adjustment. For 9 current carrying conductors, it is going to be 0.70. Now we're going to head and find our temperature correction. In this case, it's 0.91. Now we're just going to take and bear out the math. We take our original ampacity, multiplied by the bundling adjustment, multiplied by the temperature correction, and we're going to find our new allowable ampacity, which is 60.51 amps. And we're going to select C. Great job. All right, guys, that's it for this week. I just want to take a minute and encourage you that you keep working. You can do it. It is possible. Just keep grinding. Keep working hard. You're going to make it. You're going to get it. I've got your back. Let's get to it. Hey guys, what's up? This is week 12 of the Master Electrician Exam Prep Series. I'm so excited to be a part of your journey. I can't wait to see what the future holds for you. There has never been a better time to be getting your license, to be working hard and growing in the field. Anything you need from me, you just email me at electricalcodecoach@gmail.com. This week, we're going to be getting back into bundling adjustments and temperature corrections, and then leading into something special toward the end. Let's go ahead and get to it. Woo! What is the allowable ampacity of a 4-aught THWN-2 copper conductor that's installed in a pipe with 3 current carrying conductors in an area with an ambient temperature of 115 degrees Fahrenheit? When we're doing our temperature corrections and bundling adjustments, we always start with our original ampacity in the 90 degrees C column. We're going to find out that 4-aught in the 90 degree C is good for 260 amps. Now let's start with our bundling adjustment. So we're going to head to those respective tables, and we're going to find out that for 3 current carrying conductors, there is no bundling adjustment, so we can move on. Now we're going to head to our temperature correction table, and we're going to find out that for 115 degrees Fahrenheit, it's 0.82. Then we're going to take our original ampacity of 260, multiply it by 0.82, and that's going to give us a new allowable ampacity of 213.2 amps. And we select A. Great job. What is the allowable ampacity of a 250 kc mil THWN-2 copper conductor that's installed in a pipe with 9 current carrying conductors in an area with an ambient temperature of 148 degrees Fahrenheit? When we're doing our corrections and bundling adjustments, we're going to start in the 90 degree C column. We're going to find that 250 kc mil in the 90 degree C column is good for 290 amps. Now we're going to head to our respective bundling adjustment table, and we're going to find out that our bundling adjustment for this, for 9 current carrying conductors, is 70% or 0.70. Then we're going to head to our temperature correction table, and we're going to find out that 148 degrees Fahrenheit is 65% or 0.65. Then we take and bear the math out. We take our original ampacity multiplied by 0.70 multiplied by 0.65, and that's going to give us a new allowable ampacity of 131.95 amps, and we're going to select B. What is the allowable ampacity of a 250 kc mil THWN-2 aluminum conductor that's installed in a pipe with 6 current carrying conductors in an area with an ambient temperature of 165 degrees Fahrenheit? We're going to start in the 90 degree C column. We're going to find out that 250 kc mil in the 90 degree C column of aluminum is good for 230 amps. Now we're going to head and do our bundling adjustments. We're going to find that for 6 conductors, it's 80% or 0.80. We're going to do our temperature corrections. We find out that for 165 degrees Fahrenheit, it's 50% or 0.50. Now we're going to take our original ampacity. We're going to multiply it by 0.80. Then we're going to multiply it by 0.50, and we're going to get a new allowable ampacity of 92 amps. Great job. And we select D. What is the allowable ampacity of a number 6 THHN aluminum conductor installed in a pipe with 11 current carrying conductors in an area with an ambient temperature of 32 degrees C? Starting in the 90 degree C column, we'll find our original ampacity. We find out that number 6 in the aluminum column for 90 degrees C is going to be 55 amps. Now let's do our bundling adjustment. We're going to find that for 11 conductors, it's 50% or 0.50. Now we're going to head and do our temperature corrections. We find out that for 32 degrees C, it's 96% or 0.96. Now we take and bear the math out. We take 55 amps multiplied by 0.50 multiplied by 0.96, and that's going to give us a new allowable ampacity of 26.4. And we select B. Great job. What is the allowable ampacity of a 1-aught THHN aluminum conductor that's installed in a pipe with 8 current carrying conductors in an area with an ambient temperature of 42 degrees C? We're going to start in the 90 degree C column, and we're going to find out that 1-aught aluminum in the 90 degree C column is good for 135 amps. Now we're going to do our bundling adjustments. We find out that for 8 current carrying conductors, it's 70% or 0.70. Now we're going to do our temperature corrections. We find out that when we're dealing with 42 degrees C, remember we have to make that distinction. When you're dealing with Celsius, you're going to start on the far left-hand side, go down and find your ambient temperature, and then you have to come all the way back across to the 90 degree C column and make sure that you select the correct factor. And we're going to do 87% or 0.87. And we're going to take the original opacity of 135. We're going to multiply it by 0.70. We're going to multiply that by 0.87, and that's going to give us a new allowable ampacity of 82.215 amps, and we're going to select C. All right, let's go ahead and switch gears in the program. We're going to switch into the optional method. I gave us a break after doing the standard method calculations, and I wanted us to kind of just take a break from doing load calculations. Now we're just going to refresh on the optional method. I want you to know both of them. Thankfully, the optional method is a lot easier, and we'll probably finish this week and then dive all of next week into the optional method. So we're going to be in 220.80 leading into 220.82. Let's get to it. All right, we're going to do a general lighting demand calculation before demand factors. So we're just going to be dealing with the square foot VAs and the small appliance VAs. One thing I do want to note when you're doing the optional method, all of this original part is exactly the same as doing the standard method. So we just change gears. It's when we apply our demand factors and do our appliances that the game really changes. So let's go ahead and just refresh. What is the total general lighting demand before demand factors for a dwelling unit that has 4,300 square foot of main living space, a 400 square foot sunroom, and an 1,100 square foot detached garage? So we're going to total the total square foot in our calculation. We will count the 4,300 square foot of main living space. We're going to count the 400 square foot of sunroom, and we're going to omit the 1,100 square foot of the garage. It's the same principle and the same rules as if we were doing the standard method. So we're just going to take that and we're going to multiply it by 3 VAs per square foot. We're going to bear that math out, and that's going to give us the 4,700 square foot. And then we are going to go ahead and multiply that by 3, and that's going to give us 14,100. Now what we're going to do is we're going to have to add in the 4,500 VAs for the small appliance. So all of the same process, all of the same rules, all of the same steps up until this point, and we just add those two together, and that gives us a total general lighting demand of 18,600 VAs, and in this case we're going to select B. Now let's do another one, and we're going to do the demand factors. So it's going to be the same process as doing the standard method right up until we input what the demand factors are. Same process, different inputs. Let's go ahead and jump into it. What is the total general lighting demand after demand factors for a dwelling unit that has 3,300 square foot of main living space with a 400 square foot front porch and an 1,100 square foot attached garage? So first we're going to determine the total square foot that's included in our calculation. We will count the main living space, we're going to omit the front porch, and we're going to omit the 1,100 square foot garage. So we do it at 3 VAs per square foot. So we take that 3,300 multiplied by 3, that's going to give us 9,900. Then we're going to take and add in our 2 small appliance and 1 laundry circuits. So we take that and add that all in, and that's going to give us 14,400. Now this is where things change a little bit. We're going to head to 220.80, and their demand factors are a little bit different percentages. Same process, different percentages. So we take the first 10,000 at 100%, and we're going to take the remainder at 40%. That's it. So we take our 14,400, we minus 10,000 right off the top, and that's going to give us 4,400 left to apply the demand factor to. So we take that, we multiply it by the 40%, and that's going to give us 1,760. Now we have to take and add back the original 10,000, and that's going to give us 11,760. And we're going to select A. I love the optional method. It's a lot easier to work and deal with. Now, next week, we're going to pick up and we're going to jump into dealing with the appliances. And then we're going to work for that week, work together, and then we're going to put it back together into one piece, into one whole home. And, we're going to do a commercial one as well for the optional method. Let's go ahead and get to it. Thank you so much for joining us. That wraps up this week. I'm really excited to be a part of your journey. You can join us next week when we pick up diving deeper into the optional load calculations. This program is designed to help you get farther and farther and go as high as you want to go. I'm here to help you every step of the way. I offer 100% free coaching to anybody who needs it in life or business. I'm the Electrical Code Coach. You can email me at electricalcodecoach@gmail.com. Let's get to it. Hey guys, what's up? It's the Electrical Code Coach, and this is week 13 of the Master Electrician Exam Prep Series. This week we're going to be dealing with optional load calculations and diving farther into it. I'm thankful that you've allowed me to serve you this week. I can't wait to see what the future holds for you. Let's go ahead and get to it. All right, let's start slow. We're going to get our feet wet, and then we'll dive deep in. So let's deal with appliances. So what is the total VA before demand factors for the following appliances using the optional method? The nameplate ratings of a 1,500 watt dishwasher, a 1,200 watt garbage disposal, a 1,100 watt central vacuum system, and a 5,000 watt water heater. Now remember, when we're doing the optional method, there is no 4 or more 75% rule. What we're actually going to do is we're going to use the nameplate rating of each appliance. So we're going to take 1,500 plus 1,200 plus 1100 plus 5000, and that's going to give us a total of 8800. Now here in a few slides we're going to learn how to apply the demand factor to that again, but this question was asking what is the total before demand factors. So in this case we take it at the nameplate rating and we're going to select B. Great job. What is the total VA before demand factors of the following appliances using the optional method? The nameplate ratings of a 1400 watt dishwasher, 11 kW range, a 4800 watt dryer, and a 4500 watt water heater. So we're not going to use the 4 or more 75% rule because it doesn't apply in the optional method. When using the optional method, we're going to use the nameplate ratings of the appliances. So we take them, we just total them up. Again, this question asks for the VA before demand factors, and we're going to select C. What is the total calculated load after demand factors for a dwelling unit that has 3,300 square foot of main living space with the following appliances? A 1400 watt dishwasher, an 11 kW range, a 4800 watt dryer, and a 4500 watt water heater. So we're going to take our square foot, we're still going to multiply it by 3 VAs, and that's going to give us 9,900. Now we must add our 2 small appliance and 1 laundry circuit calculated at 4,500 VAs. We're going to take and add those together, and then we're going to set them over and start a larger math problem. We're going to apply the demand factors for optional method pretty much all at the same time, excluding the AC and the heat. So now we're going to take 1,400 plus 11,000 plus 4,800 plus 4,500, and that's going to give us 21,700. Remember, we're just taking the nameplate values of all of these appliances. We're going to add that to our larger math problem. Now we're just going to total that out. That's going to give us 36,100 VAs. And so this is how the demand factors work. You can find it in 220.82. When we're doing the optional method, we're going to take the first 10,000 VAs at 100%, just like we did before with the standard method, but it was a smaller amount. Then we're going to take that remainder at 40%, and then we're done. It makes it a lot simpler. So we're going to take that total of 36,100, we're going to set aside our 10,000, and that's going to give us 26,100. Then we're going to take that remainder, multiply it by the demand factor, which is 0.40, and that's going to give us 10,440. Now we're going to take that 10,000 that we took and set to the side, and we're going to add it back to our reduced load. And that's going to give us a total of 20,440. And we are going to select A. Great job. What is the total calculated load after demand factors for a dwelling unit that has 4,500 square foot of main living space with the following appliances? An 1,100 watt dishwasher, a 13 kW range, a 5,200 watt dryer, and a 3,500 watt water heater. So we're going to take 4,500, multiply it by 3, which is our VAs per square foot, and that is going to give us 13,500. Then we're going to take and add to that our 2 small appliance and 1 laundry circuit at 4,500 VAs. We're going to take and add that all together, and then we're going to start a larger math problem over here to the side. Now we're going to take all of our appliances and total them together. So we take 1,100 plus 13,000 plus 5,200 plus 3,500, and that's going to give us a total of 22,800. We're going to take and add that to the side. Now we need to add those two together. That's going to give us 40,800. Now we're going to head to 220.82 and we're going to apply our demand factors. So we're going to take the first 10,000 at 100% and then do the remainder at 40%. So we take that 40,800, we're going to burn 10,000 and set it to the side, and we're going to be left with 30,800. Now we're going to take that 30,800, we're going to multiply it by 0.40, and that's going to give us 12,320. And we are going to take our original 10,000, we're going to add back our reduced load, and that's going to give us a total of 22,320. And we are going to select D. Great job. What is the total calculated load after demand factors for a dwelling unit that has 1,200 square foot of main living space with the following appliances? A 1,000 watt dishwasher, a 9 kW range, a 5,000 watt dryer, and a gas water heater. So we're going to take and first figure out our square foot VAs. We take 1,200 multiplied by 3, and that's going to give us 3,600. Now we take and add our 4,500 VAs for our 2 small appliance and our 1 laundry circuits. So we're going to take and total those together, and we're going to start a larger math problem over here to the side. Now we take the total of all of our appliances. In this case, they have a gas water heater, so that's not going to be a consideration for us in the load calculation. So we just take the known appliances, we add those out, and that's going to give us 15,000. So we take and add that over to the side. Now we're going to take and total that out. That's going to give us 23,100. Now we're going to do our demand factors. We are going to take 10,000 and set it to the side. So we take our starting total, we minus 10,000, and that's going to give us 13,100. Now we take 13,100, multiply it by the demand factor, which in this case is 0.40, and that's going to give us 5,240 VA in our reduced load. Then we're going to take 10,000, we're going to add back the reduced load, and we are going to get 15,240. And we're going to select A. Great job. When doing heating and cooling using the optional method, we're going to select from the larger of the 6 choices that are listed in 220.82c. So we're going to pick the largest one. If your question lists multiple, you got to factor both of them and then select the largest one. So you're going to calculate the AC at 100%, and if it happens to be the largest load, you're going to select it. Or you're going to select 100% of the heat pump if there's no supplemental heat, either no strip heat or no baseboard heaters anywhere else in the house, any other type of fixed, electric heating or something like that. Or you're going to do 100% of the heat pump plus 65% of supplemental heat if it's installed. In our area, they will do a heat pump and they'll do what's called a heat strip, which is built right there in the unit, and you would add 65% of it. I love the way the optional method does it. It makes it very clear. So I'd factor in the heat pump, whatever that was, and then I would take the heat strip and I would do it at 0.65, and that's going to be my total. And if it's larger than any one of these other calculations, then that would be the one that I would select. Okay, if you're doing electric space heating with 4 units or less, it's going to be 65% of that. So if after totaling that and multiplying it by 0.65, if that ends up being a larger load than your AC, then you're going to select it for your load calculation. And you're only going to be required to do 40% of electric space heating when you have 4 or more units. Now, next week, we're going to dive deep into this, right? So what we're going to do is I'm going to try to break down every one of these variations of questions and just take it piece by piece just so you thoroughly understand it. Some of these things you may not be tested on, but this is not just about testing. This program here is about you becoming a master electrician and understanding what's going on. So there's going to be some things that we cover that, you may not use, on your test, but you very well may use them in real life. Or it's going to be 100% of some type of thermal storage heating. So if you're out in the field, you're in an area that's doing the thermal storage heating or any of those type variations, then you calculate it at 100%. And if it's the larger of the 2 between it and the AC, then you're going to select it for your load calculation. So I'm very excited to jump into next week. I can't wait to see what it holds. Hey guys, that's it for this week. I'm very thankful that you allowed me to serve you this week. If there's anything I can do for you in life or in business, please email me at electricalcodecoach@gmail.com. I just want to add value to you and help you in any way that I can. Be everything that you can be in life and in the electrical industry. Let's get to it. Hey guys, welcome back to week 14 of the Master Electrician Exam Prep Series. This week we're going to be dealing with optional method heating and cooling load calculations, and then we're going to be leading right into motors. I'm very excited. Let's get to it. All right, so when we're doing heating and cooling using the optional method, we're actually going to select the larger of the 6 choices that are listed in 220.82c. And it'll be any one of the following, whichever one is the largest. So 100% of the AC, 100% of the heat pump if there is no supplemental heat, 100% of the heat pump plus 65% of the supplemental heat if installed, 65% of electric space heating with 4 or less units, baseboard heating would be a good example, and 40% for electric space heating that has 4 or more units. So we're going to cover an example of all these. The only one we're not going to cover an example on is 100% of thermal storage heating. You're probably not going to get that question. If you do, you just take it at 100%. And if that is larger than the AC, which it's likely going to be, you're going to then go ahead and, use 100% of it. So it just depends on where you're at, geographically, and, but we're not going to cover that on the example questions today, but we are going to cover the other 5 options. So let's get to it. Okay, so let's look at variation 1. This is going to be 100% of the AC or 100% of the heat pump if there is no supplemental heat. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor rated at 22 amps and a heat pump compressor rated at 25 amps, both using a 2.2 amp blower motor on a 120/240 volt system using the optional method? So first we're going to calculate the AC. So we take our 22 amps multiplied by 240 volts, and that's going to give us 5,250 VAs. Now we're going to take and multiply out the blower motor. And so it's 2.2 multiplied by 240. That's going to give us 528. Now we just take and add those two together, and that is going to give us our total AC load. Now let's go ahead and calculate the heat. So we're going to take 25 and multiply it by 240, and that's going to give us 6,000 VAs. Then we're going to take and this is going to be our largest motor, we're assuming, in this calculation. I have you guys do that just for good practice, and that's going to give us 6,000 multiplied by 1.25. That's going to take that up to 7,500. Then we're going to add in the blower motor, and that is going to give us another 520 VAs. And then we take and add that all together, and that's going to give us 8,028 total heat. Remember, in this case, we select one or the other, the larger of the two, and we are going to select A. Great job. All right, what is the total HVAC demand you would calculate for a dwelling unit with an AC compressor at 22 amps and a heat pump compressor at 25 amps with a 10 kW heat strip, both using the 2.2 amp blower motor on a 120/240 volt system using the optional method? So we're going to use the same number for the AC through all these calculations. Almost in every case, the heat is always going to be larger, but still bear the math out. So we bear all the math out, we end up with the same conclusion, and we end up with that number. Now let's deal with the heating. So we have to take 100% of the heat pump plus 65% of the supplemental heat and add those two together. So we're going to take the heat pump, we're going to take and multiply that by 1.25. Then we are going to take our 10,000 kW heat strip, and we're going to multiply that by 0.65. Then we are going to take the blower motor, and then we're just going to add all those together. So we take the 7,500 plus the original blower motor, plus we add in now the reduced load for the heat strip, and that's going to give us a total of 14,528, and we are going to select the larger, and we select C. Great job. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor that's rated at 22 amps, using a 2.2 amp blower motor and 3 baseboard heating units rated at 3,500 watts each on a 120/240 volt system using the optional method? So we go ahead and work out the AC, and now let's calculate the heating. So we take 3, which is the number of baseboard heaters, and we're going to multiply it by the wattage. That's going to give us 10,500 VAs. Now what we're going to do is we're going to be allowed to add a 65% demand factor to that, and that's going to reduce the load down to 6,825 VAs. And you still see that even with this reduced load and such a small number of baseboard heaters, that the heat still ends up being the larger load. So we're going to select the larger, and we are going to select B. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor rated at 22 amps, using a 2.2 blower amp motor and 5 baseboard heating units rated at 3,500 watts each on a 120/240 volt system using the optional method? So first we're going to calculate the AC. We're going to break that down just like we did in the previous examples, and we are going to calculate the heat. Now we take 5 and multiply that by 3,500, and that's going to give us 17,500. Now we're going to take that and we're going to apply the 40% demand factor. So we take the 17.5 multiplied by 0.40, and that's going to give us 7,000 VAs. Now we're going to select the larger, and we are going to select D. One thing I want to note to you very quickly, and it's kind of a weird catch when you do the 4 or more or the 4 or less, because if you noticed in the last example, we only had 3 baseboard heaters and the total VAs were 6,825. Well, we added 7,000 more watts by adding 2 more of those units, and it only brought, with the demand factor being allowed to be 40%, it only brought that total demand up 175 VAs. Now that's that little pocket right there, in between 3 and 5 heaters where it doesn't change the demand much because they allow you to do such a larger demand factor. So remember, it was 3 heaters at 3,500 VAs, and it gave us a total of 6,825, and then 5 heaters at 3,500 VAs only gave us a total of 7,000. So that's pretty neat right there in that pocket right there. So let's get to it. Okay, so just to recap, remember you're going to select the larger of the 6 of the AC, 100% of the heat pump if there is no supplemental heat, 100% plus 65 if there is supplemental heat, 65 for 4 or less, 40% for 4 or more, 100% of thermal storage heating, and remember you can find all of this in 220.82C right there in the optional method breakdown. All right, now let's switch gears for probably 4 or 5 weeks, and we're going to get into motors. We're going to be dealing with conductors, overcurrent, short circuit, ground fault, overload, short-term duty, all of these fun things, but we're going to start off with sizing wires. So let's go ahead and jump into the next slide where we're going to be talking about just some of the things that we have to refresh on to make sure that we are ready to size wire for motors. Let's get to it. All right, so we're going to recap on some things to remember about sizing motor conductors. There's some rules that we have to abide by, and if you go back to week 8, part 1 of the original free 10-week series, it'll walk you through those steps again. Remember, everything that we're going to cover in this is just going to assume that you're already testing at the master level, you've already mastered all the basic principles, and you're going through and just practicing. So if you need to go back and watch starting in week 8, part 1, it's about midway through. I'll leave a link in the description below, and you guys can go back and start working on it. So let's go ahead and jump into it. So some things that we have to remember is that when we're sizing motor conductors, we're actually going to use the motor FLC and not the FLA nameplate. Now, if they have the FLC printed on the nameplate, then you can use it. But if it's just some amperage stamped on the nameplate, or if it says FLA, then you're not going to be using it. You're actually going to be using the FLC. All right, so when we're dealing with FLC, we have to go to table 430.248 for single phase. This is assuming that you already know how to do this. If not, I have tons of content teaching you how to use that table. And it's going to be table 430.250 for 3-phase. So just keep that in mind. Also, the other thing that we have to remember is that we're always going to multiply by 1.25 that FLC when we're sizing motor conductors, unless there's a duty cycle listed. So if there's a duty cycle, it says intermittent use, or it's going to be used for 15 minutes, or it's going to be used for 3 minutes, or whatever it is, then we're going to abide by and play by some different rules, and we're going to dive farther into that next week. I'm very excited to get with you guys. I can't wait to get to it. We will see you next Saturday at 6 p.m. Let's get to it. Hey guys, that's it for this week. So join us next week where we dive farther deep into motors. This channel is designed to help you become everything that you can be in life and in the electrical industry. If you need anything, you can email me at electricalcodecoach@gmail.com. Let's get to it. All right, guys, I'm super excited about this week's videos. We are in the Master Electrician Exam Prep Series. We're in week 15, and this week we're going to be dealing with motor conductor sizing. Let's get to it. All right, guys, just a quick recap. Things to remember when we're dealing with motor conductors. When we're sizing it, we're going to use the motor FLC, not the FLA nameplate primarily, and we're going to break that down as we go through. We're going to use table 430.248 for finding the FLC for single phase. We're going to use table 430.250 when we're doing 3-phase, and we're going to multiply the FLC by 1.25 unless there's a duty cycle listed or there's a couple other parameters that we're going to look at here in just a minute. This week we're going to be practicing normal motor conductors only, and next week we're going to jump into duty cycles and some of the other variants that you may see on the master exam. What size copper conductors would you select for a 3 horsepower, 208 volt, 3-phase motor that has an FLA nameplate of 9 amps terminating to 75 degree C terminals? Remember, when we're sizing normal motor conductors, we're going to use the FLC. For conductors that have motors that are 1200 RPM or less, intermittent duty, multi-speed, or for high torque, you will use the nameplate current rating. I just want you to have that in the back of your mind. This week, and when you're dealing with normal motor conductors, we're going to use the FLC and not the FLA nameplate. When we're dealing with a certain special sect of motors, we will actually use the FL nameplate. I wish the code book wasn't like this. I wish they would just pick one or the other and just stick with it because it makes it very hard when you're testing. But I'm going to teach you this week and reteach you because remember we've learned this in the past. This is the Master Series. This is all about you already knowing this much, but I do want to recap so it's fresh on your mind, right? All right, so let's go ahead and jump in. All right. Also, when we're doing normal single motors, we're going to multiply that FLC by 1.25. We're going to be doing some multiple motor questions next week, but this week we're going to be doing all single motors, meaning one motor, and we're going to be doing normal conductor sizing. So let's go ahead and jump in. All right, so back to our question here. First, we're going to find our FLC listed in 430.248 for single phase and 430.250 for three phase. Well, in this question, our question's three phase, so we're going to head over to 430.250. We're going to slide down on the left and we're going to select our respective horsepower. Then we're going to tee off in the right for our respective voltage. Make sure you use a piece of paper so you don't get off, and you tee off at 208 volts. And we're going to find that our motor FLC for this motor is 10.6 amps. All right, now we have to multiply it by 1.25. So we're going to take 10.6, multiply that by 1.25, and that's going to give us a new amp draw of 13.25. That's going to be the amperage that we size our wire by. Okay, so we take that 13.25. Now we've got to head to our primary ampacity table. You're going to be in 310.15B16 in the 2017, and you're going to be in table 310.16 in the 2020. What we're going to do is we are going to head to the 75° C column. When you are dealing with motors, you are going to select the conductors based on whatever the terminal rating is. So if it says 60, 75, or 90, whatever it states, that's what you're going to be selecting from for your question. All right, let's go ahead and jump right into it. In this case, we come down, we find that a 14-gauge wire in the 75° C column is good to cover our 13.25 amps, and we select A. Great job. What size copper conductors would you select for a 5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 15.2 amps terminating to 75° C terminals? I want to note that they're always going to throw that nameplate rating in there to try and throw you off. All right, so remember we're sizing our normal motor conductors, so we're going to use the FLC. Okay, we recapped that previously. Also, for single motors, we're going to multiply it by 1.25. So first we're going to head to 430.250 because this is 3-phase. We come down on the left-hand side, and then we're going to select our horsepower. Then we come across the top, we're going to select our voltage, and then we're going to tee off and find out that this motor's FLC is actually 16.7 amps. Now we're going to take that 16.7, we're going to multiply it by 1.25, and that's going to give us a new amp of 20.87. Now we are going to head to our primary ampacity table for the 75° C column. So we come down on the left side. Actually, I would come down in the middle and just look for your amperage. And then we'll come back over and kind of work the table backwards. So we'll start in the 75° C column and come down until you find a wire that covers 20.87 amps. All right, so we come down, we find it, then we go and tee over to the left, and we're going to find out what size conductor it was. And in this case, we find out that it is a number 12 conductor, so we're going to select B. Great job. What size copper conductors would you select for a 7.5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 28.6 amps terminating to 60° C terminals? So we're going to go through our initial steps here. Then we're going to head to table 430.250 because we're dealing with 3-phase. And we're going to go down on the left-hand side and find our horsepower. We're going to come over and tee off with our voltage, and we're going to find our motor's FLC. And in this case, it's going to be 24.2 amps. Now we have to take that 24.2 amps and we're going to multiply it by 1.25. That is going to give us a new amp draw of 30.25 amps. Now we're going to head to our primary ampacity table. And this is where we have to be careful. Our question states that we're terminating to 60° C terminals. So we have to be sure to head to the 60° C column. So we're on the left-hand side. We go down in our 60° column until we find a wire that is going to cover our amp draw. And in this case, we find in the 60° C column that it's a 10-gauge wire. Great job. Let's get to it. What size copper conductors would you select for a 10 horsepower, 115 volt, single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degree C terminals? We're going to go through all of our initial steps. Then when we get here, we're going to change over to table 430.248 because we're dealing with single phase. So when we head there, we do the same process. We find our horsepower, we come over to our voltage, and we're going to find out that this motor has an FLC of 100 amps. Now we have to take that 100 amps and we're going to multiply it by 1.25, and that's going to give us 125. Now we head to our primary ampacity table, and again we're back in the 75 degree C column for copper. We're going to come down until we find a wire that is large enough to handle our 125 amps, and we're going to select D. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has an FLA nameplate rating of 47.5 amps terminating to 75 degree C terminals? So we're going to come down here, we're going to go through all of our initial steps, being sure that we head to table 430.248 for single phase. When we get there, we're going to come down, we're going to do our process, and we're going to find out that this motor's FLC is 50 amps. Now I wanted you to notice that I did the same size motor as far as horsepower, and we doubled the voltage and took it to 430. And when you do that math, it cuts our amp draw in half. So I want you to think about that as we do this problem. So this motor's FLC is 50 amps because we doubled our voltage. Now we're going to take that 50 and multiply it by 1.25. That's going to give us 62.5 amps. Now we're going to head to our primary ampacity table in the 75 degree C column, and we're going to come down and we're going to size our wire to a number 6 gauge. So I want you to notice when we doubled the voltage, it cut our amperage in half, which allowed us to size our wire in half. That is the advantage of two wires containing, two hot phase conductors, is it's going to cut your amp draw in half if all things are equal, okay? In the same way that 3-phase ultimately does the same things, all things being equal. So it's just one of those things that how you can reduce the load, which ultimately allows you to reduce the wire, which ultimately allows you to reduce the pipe and all the other things, considered. So I hope you guys enjoyed that one. What size copper conductors would you select for a 10 horsepower, 230 volt single phase motor that has a nameplate rating of 47.5 amps terminating to 60 degree C terminals? Now I went through on this one and I basically did the exact same problem, and I went through, but I wanted just to show you the difference of the 60 degree C terminals. So we went through, we found our motor FLC, we multiplied that out, ended up with the same result, but now we have to head to our 60 degree C column. See, previously our wire was a number 6 wire. Now let's look what happens when we head to the 60 degree C column. We're going to find out that we actually have to upsize it to a number 4. So sometimes it can make a significant difference when you're having to terminate to certain terminals, but I just wanted to kind of bear this out and show you. But always go through, carefully read your question. These motor questions are something that you have to slow down and apply like 50 different rules to, and just carefully select your conductors. What size aluminum conductors would you select for a 10 horsepower, 115 volt single phase motor that has an FLA nameplate rating of 95 amps terminating to 75 degree C terminals? All right, so we're going to go back through, we work through, we make sure that we head to table 430.248 because we're dealing with single phase. Then we head over and we tee off and we find out that our motor has an FLC of 100 amps. So we're still going to take that and multiply it out by 1.25, giving us a new amp draw of 125 amps. Then we have to watch out here. We're going to head to our primary ampacity table, but we have to be careful. There was a subtle distinction here. Did you catch it? It's wanting us to use aluminum conductors. So in this case, we actually have to head to the aluminum side of the respective table. So we head there, we head down in the 75 degree C column, and we're going to find that we're going to have to upsize this all the way to a 2-aught, which, is, I think around 2 sizes larger than what we originally figured when we did copper. So that's the difference there. So I really enjoyed this week with you guys. Let's get to it. All right, guys, you've made it through another week. That's what this is all about. Practice, practice, practice. I'm so thankful I get to be a part of your journey. If you want to sign up for the online testing center, you can check it out. And you can also check out, we just dropped a 400 question test PDF download series. If you haven't checked it out, I'll put a link in the description below. I hope you guys have a great week. If there's anything I can do to help you in life or in business, you can email me at electricalcodecoach@gmail.com. Let's get to it.